What I'd like to do in this video is talk about series expansions in the context of classical mechanics. Let's say that you're solving a projectile motion equation and you get to this place where you have the maximum, or the time to maximum position in terms of itself. In terms of itself. What can you do? Well, that exponential might be a little tricky, but we could use a series expansion to help us out. So if I have e to negative epsilon, I can expand that to second order as 1 minus epsilon plus epsilon squared over 2. It's a little bit of an intuitive sense of when you stop your series expansion. Basically, if you know that epsilon is small, then as the powers get bigger, epsilon gets very, very small. And so our error, and this is pretty cool, our error here would be of order epsilon cubed. So you basically just need to figure out how much error you're willing to accept. And if I went to the third term, our error would be order epsilon to the fourth, and so forth. And in this case, our epsilon is ct over m, just looking back at the original equation. And I'm going to flip to a clean page, so pause if you want to write anything down. And if I just substitute now using the expansion I just did, this is what I get. It's a bit messy, but really it's just taking that epsilon and substituting it in. And now I'm just trying to simplify things down. I will pop up the lines as I go briefly, so if you want to take a look or pause. So if you want to convince yourself that my first line equals my second line, just pause for a second and do that. Otherwise I'm going to move to a new page and continue simplifying. Here is the next line in my simplification. Again, if you want to convince yourself that's right, go ahead. I'm going to add one more line on this page. And I get to a place, now if I move the Tmax that was on the other side of this equal sign over, I get to a place where I can find the roots of the equation. So now that I'm here, there is an obvious Tmax equals 0 solution, and we're going to ignore that. The second solution, then, I will show you on the next page. So if you were looking at that and trying to solve it, you probably realize that the solution is going to be pretty messy, and it is about as messy as you'd expect. I can combine those two fractions in the bottom to try to simplify this a bit. So if I find a common denominator and add them together, I can simplify down to this expression. And we can make this just a little bit simpler using another series expansion. So if you want to write this down, I'm going to move to that series expansion on the next page. So you have a very small x in expression 1 plus x. We can say that's about 1 minus x. So imagine if x is like 10 to the negative 15th. Then this seems fine. It's basically indistinguishable from 1. And if we do the series expansion of 1 minus x on this, then we can arrive at this expression. Now hopefully you get enough practice with series expansions that you kind of learned when to use them and recognize the situations where they're helpful. But this is an example in the context of classical mechanics.